Membrane potential is basically, as it says here, the difference between the electrical content inside the cell and outside the cell. Okay. That's never a good sound. Okay, between inside and outside. Now for neurons, the resting potential is minus 70. On this picture, you've got an electrode that is going into the cell, and you have an electrode that is remaining outside of the cell, and you're measuring the difference. Okay. Now, inside the cell, potassium and phosphates, there's also magnesium here, but I highlighted potassium and phosphates. They are going to be in large numbers inside the cell. Outside the cell, sodium and chlorides, and again, there are other things here, but those are usually the big ones that we want to look at. They're in higher numbers outside. Typically, inside is more negative than outside. That's where we get our minus 70. Because of diffusion, potassium tends to leave the cell interior, making it more negative. And you can see it's a big arrow compared to sodium that's coming in. And that's because there's so much more potassium inside the cell than outside. And so because of that concentration gradient, it wants to move outside. Right, so there's always going to be a little leakage, potassium going outside, sodium coming in. Trying to bring things back to normal, homeostasis, we've got a sodium-potassium pump, which is exchanging the sodium and the potassium. Trying to keep things at rest. All right? Okay, now for action potentials, we have to consider our gates, our gated channels. There's two types of gated channels. One is electrical or voltage gated, and the other responds to chemicals or ligands gated. And in our case, we talk about transmitters. Now, as neurons communicate to each other, they are sending electrical signals, and they are sending transmitters. But the potential at the area of the dendrite and soma usually isn't big enough to create an action potential. Okay. Until it reaches the axon hillock. At the axon hillock, that's where the axon meets the soma. That's where a lot of, especially electrical currents, peak and are able to then open up channels. Okay, action potential, excitatory stimulus, and this is going to be voltage gated. Opens up sodium channels. A little bit later, the potassium channel is open. When you get down far enough, I think this is actually our pump. When you get down far enough, you can start getting calcium to come in, which moves our synapses towards, our vesicles with the transmitter towards the synapse and have it released there. Right? But simply, as far as the action potential, voltage-gated sodium first, then voltage-gated potassium. Again, I thought I had another picture up here, but it's not. But all the sodium coming in is what's going to increase. Here you go. All the sodium coming in is going to increase the potential, make it less negative. Okay. As it goes up, it opens up potassium channels, which is allowing the potassium to come back in, making the inside less negative, more negative, and bringing back, repolarizing the cell. It usually overshoots. The sodium channels are open for a short period of time. Potassium channels are open longer. So there's usually a little bit of an overshoot called an after potential. Makes it harder to stimulate the neuron. Okay? So that's sort of the crux of it. Now the next thing you mentioned was, and you can see we've got more slides on that. Next thing you mentioned was muscle. I believe that was week 2. Okay. At the neuromuscular junction. I can set the slideshow so you can see the right? So you see the current coming down, causing vesicles to open up and release transmitter. At the muscle membrane, we've got the receptors. What transmitter is this? Acetylcholine, yeah. Good, you remember. Okay, and here's your neuromuscular junction. On the neuron side, the ending is going to have a little expansion that's called a synaptic terminal or a synaptic bouton. It will contain vesicles, right? And then inside those vesicles are acetylcholine. Okay, we've got signal coming down the axon because of our myelin, it's jumping. We also have calcium channels opening up at the terminal. That's going to create enough of a potential to release these transmitters into this space. This space is called the synaptic cleft. On our muscle side, there's a trough. And inside the trough are receptors that are attached to channels. Also, we've got little extensions of membrane coming down. These are called the subneural clefts. That allows you to put more receptors in, increase the surface area. Right, so we release into the synaptic cleft. The acetylcholine diffuses across to our muscle membrane, finds itself a receptor, opens up channels, and we've got a lot of sodium coming in, some potassium leaking out, and that's going to stimulate the muscle. Okay, the actual potential for the muscle is propagated down muscle fibers. Typically, when we're talking about skeletal muscles, they are too long to keep that potential going. So they have little T-tubules, which gives it a little extra surface area in order to help keep that potential up. And also, we'll have a picture coming up showing what else goes on with the T-tubules. Let's see. So we release acetylcholine, they find the receptor, they open up channels, sodium pours in, potassium out, activates muscle. There's an enzyme in here called acetylcholine esterase. Whenever you see something with esterase, that's usually an enzyme that breaks down the similarly named compound. So in this case, that will break down acetylcholine into an acetyl portion and a choline portion. That's what you see in this picture. Breaking up these acetate, choline. The choline gets reabsorbed and it's able to be recycled to make more acetylcholine. And it's able to do that relatively quickly at the terminal. It doesn't need to go all the way back up to the cell body to do this. Okay, now within our muscle fiber, and again, this is skeletal muscle fiber, we have actin and myosin, and on the outside, we've got sarcoplasmic reticulum. For skeletal muscles, sarcoplasmic reticulum is going to store calcium. Okay, when the potential gets high enough, let's see, I know I have that picture. There's our T-tubule. When the potential gets high enough, this DHP, dihydropyridine, is going to open up calcium channels to allow calcium to flow out of the sarcoplasmic reticulum. Calcium is going to attach to tropomyosin and troponin complex. Tropomyosin and troponin. The tropomyosin and troponin are going to block actin binding sites. So if the troponin-tropomyosin complex is there, we can't attach myosin to actin. Calcium removes that. Calcium opens up those binding sites. Okay, so our calcium's being removed from our sarcoplasmic reticulum, from energizing this DHP receptor, so our calcium comes out. Opens up binding sites by removing troponin and tropomyosin. And it just moves it a little bit out of the way, just enough to open up those binding sites. It's not like it takes it completely away, so that it disappears. And binding happens. The heads of the myosin will bind to the actin. These heads then sort of hold the actin open. That's called the sliding filament theory. It was proposed by the Huxley and Huxley. Okay. So we remove the troponin because of calcium. Opens up the binding sites on actin so the myosin heads can attach. ADP releasing, ATP releasing the phosphate creates energy that allows the phosphate to attach to our myosin head, helps with attachment to the actin. The ADP drops off, and the myosin head again folds the actin over. This is called power stroke. ATP reforms. You've got loose phosphate, and the ADP is going to reform to ATP. If you have ATP present, that's going to cause the myosin heads to inactivate, drop off the actin, and you start again from scratch. Right? So cyclical process. Okay, now with smooth muscle, instead of troponin, you've got what? Smooth muscle instead of troponin, what do we have? Calmodulin. Calmodulin. I know you're all thinking it. Right? So that's a big difference. You know, besides that, they both have the actin, the myosin, works similarly. With the skeletal muscle, most of the calcium came from inside, from the sarcoplasmic reticulum. When you look at smooth muscle and cardiac muscle, most of the calcium is coming from the extracellular fluid. Although with cardiac muscle, you still do have a good amount of calcium coming from sarcoplasmic reticulum. It is not as much as what we see with the skeletal muscle. Okay. Questions? You good? All right. Questions? Okay. Look at pictures, look at drawings, especially for some of this mechanical stuff. Maybe it helps. I'm a big one for drawing things out. Questions? You know everything? So, okay. I know your mind is elsewhere. So, if you have questions, you can stay. If you don't have questions, you can leave. And again, those, I did put the review PowerPoints up, so they're available, but they're just the same as your individual PowerPoints.